Hi guys, good to see you again. We are continuing on with entropy today. You hopefully would recall from our last presentation, sorry, easy word, totally lost my mind. Hopefully you recall from our last presentation a little bit about entropy and how it deals with disorder in a system and how the universe is constantly expanding, and that is a certain value of entropy that we need to think about, positive versus negative. Hopefully this comes back a little bit. We're going to keep going on delta S a little bit today, and then it says here on the front screen we're going to work with something called free energy. So a little bit of a continuation from yesterday, and then you're going to get some snippets of new information also today. Now, it's not a typo that it says first we're going to do 16.5 and then we're going to do 16.4, and I promise that's not just a crazy Seagrave thing, but it actually makes sense. I don't know why they put this 16.4 in front of it. If I wrote the textbook, then I would have done it differently. So I guess I have that option at this point. So this is, again, out of your Chapter 16 supplement, the Zoomdoll 7th edition. And you may want to turn in that packet to page 763, as that is going to be one of the first pages that we'll talk about. So here we go. So 16.5, talking about entropy changes in chemical reactions. What I want you to note from the information that's here on the screen is that you will be asked to do tasks that ask you to predict the spontaneity of a reaction. And remember that the word spontaneity has nothing to do with speed, whether it's too fast or too slow. Instead, it really should be termed, as AP appreciates it, thermodynamically favored. So to say that a reaction is spontaneous means that it's thermodynamically favored, meaning that if you get the reaction started, it continues on its own. So in the example here, you can see that we have nitrogen gas and hydrogen gas, and we're producing ammonia. And underneath it, I have a count here of molecules. I say 4 molecules on the reactant side and 2 molecules on the product side. And that's probably pretty easy to understand just based on coefficients and thinking in terms of total molecules, which again kind of goes back to the whole thing we were doing with breaking bonds and things like that, drawing out basic Lewis structures or skeleton structures. So this is going to be one relatively simplistic option for how to predict, based on entropy, whether a reaction is likely to be spontaneous or thermodynamically favored. So because you go from 4 molecules down to 2 molecules, we would predict the sign of our entropy, or our delta S, to be negative. Because we go from 4 molecules to 2 molecules, that's going from more stuff flying around to a connection of the stuff to make less stuff. So if you have 4 people running around crazy and then you partner them up and now you only have these 2 smaller groups, it's getting less disordered. So less disorder means less entropy, and that would lead to a prediction that it would not be a spontaneous reaction, or that it would not be a thermodynamically favored reaction. Couple rules to live by. When you're asked to do things like this, look at a reaction and predict based on entropy alone whether it would be spontaneous or not, you're going to look at these 3 bullet points. Gases, first off, are more disordered than other states of matter, and that's something we talked about the other day. So if you're doing a reaction in which you start with a solid and then you create a liquid, that's going to be more disorder. And if you would start, say, with a solid and go all the way to a gas, that would be even more disordered. More complex molecules are more disordered, and this is because of ways that molecules can sometimes spin or bend. They can get connected to each other with intermolecular forces. There's a lot of options that can happen. So the more complex the molecule, the more disordered the system would be considered. And then, as we showed in this example, more molecules equals more disorder. So in the nitrogen and hydrogen example above, you're starting with more molecules and going to less, which again goes towards less entropy and less disorder, which means not a spontaneous reaction. Okay, so these rules at the bottom, you may want to write these out because they could be quite helpful to you as we continue. So if you need to pause the video, go ahead, record the yellow stuff here at the bottom as your rules to live by. Make a note card if you'd like. All right, moving on. So on page 763 in our Zoom doll supplement that I gave to you guys, I'm going to ask for you to take a look at sample exercise 16.6, and it does have the answers. So I do ask that you actually try these first, and then you can take a look at the answer. But I would ask that you just pause the video and actually attempt to determine A and B answers. Go ahead and read the answers then after you've had some time to think about it, and then I'll come back and I'll show you my answers on the screen here. Okay, so you've had a little bit of time here to try these out. In the first example here, A, we're starting with a solid calcium carbonate, and we are creating calcium oxide and calcium dioxide. This is going to be the same type of setup, that we did last time. So we start with one molecule and we create two molecules. If I asked you what type of chemical reaction this is, you might say that it's a, goodness, I want to say dissociation reaction. That's not right. Synthesis is putting together decomposition. Holy cow, sorry, total mind blank right there. Yeah, so this is a decomposition reaction where we take one reactant and form two products out of it. So in this case, you're increasing the disorder, which would be a positive sign for delta S. Whatever the value would be, it would be positive. In the second example, it is literally the opposite of what we just discussed. So you're actually going from 3 molecules down to 2, which is going to be a negative delta S because there is a decrease in disorder. Okay, so going back and thinking about something that we've actually done here in the not so distant past, we have utilized Appendix 4, which is on page A21 out of your textbook already. And you may, at this point, please do grab a textbook, turn to that page so that we can do some looking at that appendix again. But you will find also in this appendix standard entropy values, delta S values for a lot of different common substances. Remember that these are thermodynamically considered standard state conditions of the 25 degrees Celsius in 1 atmosphere. But what I'd like for us specifically to take some time with, so again, you do need a textbook at this point, is that if you are talking about the same substance but different states of matter, they will show that gases do in fact have the highest amount of disorder. And so if you would please turn to page A22 and look at the very bottom left corner where you see iodine. And I want you to note that the first 3 things listed for iodine are all I2. So it's the same substance, but if you look at the little subscript, you're going to see a different state of matter. So you see the solid and then the gas and then the aqueous. And then notice you actually have columns here. You have 3 different columns of values. And let's make sure we get the S values. So that's actually the far one. So for the iodine solid, you see a value of 116. For the gas, 261, and then for the aqueous version, you see 137. So those are in order of what we talked about. The gas has the highest value, 261, and then the liquid, the aqueous, the 137, and then followed by the solid of 116. So you can actually see that what we've been discussing is upheld by the proof in the appendix. Also note, unlike the delta H, unlike the enthalpy values that we looked at before, and again, stay on the same page here, A22, notice that iodine solid, I2 solid, has a value of 0 for the enthalpy value, but there is disorder. It doesn't have a 0S value. So as this bullet point says, note that almost all compounds have some entropy, even solids. You may note that some of them have negative entropy values, but that is generally because they're ions. So if you actually take a look at some of these, look up a little bit and find fluorine, find your F negative. So that's an ion that has a negative entropy, which is one of the reasons why it really likes to bond with things, because a negative entropy is not something that's stable. So this fluoride ion, highly electronegative, it's really not incredibly happy that way. It wants to bond up with something. So you'll notice some of those also in there. So just pointing some things out. Additionally, we kind of talked about this before. So we just mentioned the delta H values are actually in this appendix too, but you also, in that middle column, if you've noticed and maybe think I'm just like trying to pretend like we don't see it, there is this delta G value. So we will be utilizing those later, just not quite yet. So already used delta H's, delta G's are to come, and then the S values we will be utilizing within this chapter. Yippee skippy. Okay, so here's how we're going to use them. Wow. That looks familiar, doesn't it? Do you recall that there's an H equation that looks exactly like this S equation? So no joke, it is the exact same thing that we have done before, where we're going to take the sum of the products minus the sum of the reactants. Remember that the N and the M that are up here are going to go along with the coefficients from the equation. So if you go ahead and take a page turn here in your printed pages from Zoomdall 7th edition, you'll go to page 764, and at the very bottom, you'll see a sample exercise, which is the one that you see on the screen. And it also then, at the bottom of page 764, it actually lists the S values for you. So what I'd ask for you to do is, let's pretend like this is exactly the same as what it was before. We're just calculating S. And that's exactly what it is. So please take a second and pause and actually calculate it, and then I'll show you the answer. Okay, so your answer looks like this. When you start to set it up, I've taken each of the values out of the textbook part, and I've put them in just right underneath the chemical that they go to and attached the coefficient. And then here I have actually taken my products and stuffed them up here in the front, and taken my reactants and stuffed them back here and subtract everything up. And the final answer is negative 149 joules per Kelvin mole. So just notice kind of some fancy unit there on the end. And also, let's make sure that that makes sense. Okay, it does make sense, in fact, because if you take a look at the equation, we actually started off with 3 gas molecules. It was 3 oxygen molecules, and then we went down to 2 gas molecules. When you're talking about entropy and comparing molecules, you do always want to really focus on the gases, which again, guys, it actually goes back and is shown in the appendix. If you take a look at the iodines that we looked at before on page A22, did you notice that the gas entropy value, 261, was significantly higher than either one, the solid or the aqueous version? So again, when you're dealing with entropy and trying to predict the spontaneity or trying to make sense of a number, the gases really are where it's at, because those are going to have the most disorder and those are going to make the most impact. So above, you do notice that the solid molecule stayed the same, but it was the gases that actually changed. So yeah, but gases have a huge impact. Okay. All right, so now moving on to 16.4 and talking about something called free energy. So this is where you're going to see connections. We've talked about H, we've talked about enthalpy, and now we've talked about S, entropy. And we've talked about how we've got endothermic and exothermic. We've talked about thermodynamically favored. Well, let me let you in on a little secret. Everything we've talked about so far with H and S, it applies right here to something called Gibbs free energy, or usually it's shortened to just free energy. This is going to be a new equation that we're going to use, and it's similar to the one that you see in the bolded white letters here at the end. That's not the final equation though. But what free energy is, it is the G part. Gibbs, G. I think that was the guy who came up with it probably. So the H is your enthalpy, the S is your entropy, and the T would be a temperature in Kelvin. And so what you can see here is that there's a relationship between entropy, enthalpy, and temperature. In fact, what this free energy equation actually does is give you kind of the whole story. It will demonstrate that the thermodynamic favorability, so whether it's thermodynamically favored or not, it is dependent on temperature. It certainly is dependent on enthalpy and entropy also, but temperature has a pretty big impact also, and so we'll be looking a little bit at that today. This is going to be your final equation. All I did is I put triangles in front of things because there's generally a change that occurs in a reaction, and we put the little degree sign, which of course means standard state. One thing to also mention before we go on, just as you need to know signs of H and S as to what those signs mean, whether it's positive or negative, you're also going to have to know delta G signs, okay? So this is where you want to start to culminate some information. And in fact, I'm going to have you do a note card at the end of this presentation. But let me give you the quick rundown. So if you have negative delta H, that means exothermic. And we talked a couple of presentations ago that exothermic reactions are generally pretty favorable. So negative exothermic for H is a favorable condition, whereas positive H is endothermic and not generally very favorable. Okay, for S, entropy, disorder, you want positive values of S. So remember, with the H and the S, it was like opposites attract here. So if you get a positive value of S, that's thermodynamically favored, and it means more disorder. And if you have a negative value of S, that is not so favorable because it's going to be a decrease in disorder. Now for G, if the G value, if the Gibbs free energy value is negative when you would put it through this equation in the light blue box, that is a spontaneous process. Negative means spontaneous. So the G and the H have the same sort of setup. Negatives are the good ones. And then S is kind of like the guy off by himself. And that is positive is more favorable. Okay. So, and it's kind of a quick rundown, and I can create a little, easy to understand chart or something on the board tomorrow. So no big deal, but that's kind of the rundown of things you got to know. So the sample exercise, you'll have to go back a couple pages to 761, and we're going to take a look at a way of understanding delta G a little bit better, and also it's a kind of a tweak on the a tweak on the equation that I just showed you. So in sample exercise 16.5 on page 761, they are producing for you here this reaction where they're taking bromine liquid and creating a solid, and creating a gas, bromine liquid and creating a gas, and asking what temperatures will this be a spontaneous process? Basically, when will bromine liquid just spontaneously become the gas? When will it just evaporate? And then they sort of ask a secondary question, well, what's the normal boiling point? Because we haven't done anything like this, it might seem like two different questions. In fact, it's one question. The other thing that they give you, some information, they give you the enthalpy value and they give you the entropy value. Let's think before we go any further. Okay, first off, we know that for a process to really be spontaneous, or again, thermodynamically favored, it means that the delta G has got to be negative. Okay, so we know that. We also can recognize some things. Do you notice that delta H value, it's positive? Well, that means endothermic, and that's not terribly favorable. So your delta H value is saying, we might not be very favorable right now. But then notice the delta S value. That's positive. And that is the way we want it in order to have a reaction considered favorable. So your delta H and your delta S, they're actually kind of butting heads right now. And that's why this is a really good question, because if these two things are at odds, how do you figure out if it's spontaneous or not? And it all comes down to G. Okay? So, new fact. At phase changes, boiling points, melting points, whatever it is, the system that is reacting at that moment is at an equilibrium for a period of time. And one thing you'll want to know is that delta G at an equilibrium is 0. Now that's super duper helpful because we have an equation and now we can put a 0 in for it. So delta H and delta S actually will balance each other out. They'll make the G value 0. And so if we're going to find the boiling point and we know it's at equilibrium, what I can do is notice here my delta G was here and now I've just replaced it with 0. Well, if that's 0 and I do some rearranging, look at that. I've got a delta H and I've got a delta S, and they've asked me about temperature, haven't they? So a little rearranging and a little extra knowledge that you have, and you'll be able to then, do the rearrangement, and then you're going to be able to do the math because you already have two values, okay? So this is then kind of the final, ta-da of it all. But just plug it in, right? Plug in enthalpy and entropy. I have an H, I have an S, plug it in, let's do it. Please look carefully. Do you notice any problem? Any problem at all? I'm going to tell you the answer in a second, so if you're still looking, pause the video. Here's the answer. That's not a match. Sorry. The appendix in the book, and it doesn't matter what textbook you're looking at, the appendix in the book please notice, if you still have the book open, notice that your delta H values in that appendix are given in kilojoules per mole. Notice that the delta G values are similarly given in kilojoules per mole, but then the S values are given in joules. Darn it. So what this means is that you've got to do a little bit of dimensional analysis. You can't keep them this way. You have to make a match. It doesn't matter which way you go. I generally go to joules, but you can go to kilojoules. It just so doesn't matter as long as you do the math to make them match. So you can see here I've done the math to make them match. I can cancel out the various joules and moles, and I'm left with Kelvin. Fabulous. And so what I actually come up with here is 333 degrees Kelvin would be my answer to what is the normal boiling point. But then they ask, at what temperatures is it spontaneous? So this is the magic temperature. So if I have the temperature above 333, then it's going to spontaneously happen. Just think about trying to heat up water. If I get the water above 212 degrees Fahrenheit or 100 degrees Celsius, water evaporates. Ta-da! Don't have to put in much more work there. But if it's below that 333, then the process will not be spontaneous. Instead, it's going to go in the reverse direction towards the condensation. So reaction is at equilibrium at 333, and that's where the delta G value is 0 at equilibrium. Okay, so you're getting some, again, some introductory information here with this delta G, this free energy thing. Understanding at this moment that the enthalpy and the entropy are connected to it, and that temperature is a big deal. And we are going to continue to utilize these ideas as we go into the next presentation after this one, okay? So, final slide today. On page 761 at the very bottom, you will see table 16.5. And this gets at what I was mentioning earlier about all the positives and the negatives and things like that. So this table, as it says here, just read with me, relates positive versus negative, delta H's and delta S's, to spontaneity. The end-all, be-all for determining the thermodynamic favorability of a reaction lies in G. But since G is related to H and S and T, wow, that's a lot of letters. Seems like we're telling the alphabet. There's a lot to understand. So if you notice in this table, it says, it gives you two different options. It'll say, well, if this one is positive and this one's negative, or if this one's positive and this one's positive, and then it gives you the result. So reactions are spontaneous at all temperatures. Spontaneous at only high temperatures. So again, it's getting at that relationship between delta H, delta S, and T, and how they all affect G. Whew. Make a note card of this table. It is beyond important to know. The AP people on the test will pick on this a lot. This is crazy, 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 crazy important. Please make a note card. And that's it for today. We'll see ya in class.